Hi, folks. I'm Billy, and today I'm going to be presenting my work on Kishu, world's first Undoable notebook. So first, a bit about myself. I am a fifth and hopefully final year CS PhD student at the University of Illinois Urbana-Champaign. My research focus is officially on database systems, although most of my works have been outside the realm of traditional database topics, such as computational notebook infrastructure, which is why I'm here today, and also a bit of vector search. So I actually pivoted to researching these topics after starting my PhD. So prior to that, most of my undergrad work has been on recommender systems and data mining. And I am mentioning this because I use notebooks quite a lot for both my coursework and research as an undergrad student. So we will have courses like these, and then that's me. And I'll be doing something like, baby's first machine learning project in Colab and running code that may or may not work. Okay. So when I was using notebooks, there was quite a few issues that I was frustrated with, including this one. So for all the notebook users out here, how many of you have encountered something like this, where you will run a cell, it does something in place, like dropping a data frame column, or writing a variable, or just general in-place modifications, and then you immediately regret that you wish you hadn't done so. So can I see a show of hands? Great. It's good to know that I'm not alone. So I hated this. And before I go into more details, I do want to give a refresher of why this happens. So, never mind, sorry. I actually missed the last slide. So we built, because of this, we built a notebook checkpointing system called Kishu. So as you can see, the way it works is that we're currently integrated into Jupyter. So the user here ran a cell that dropped the data frame column. And basically, they can just navigate to a drop-down menu, click undo, and then that cell execution would have been undone, and the column will be back. And so, okay, now to some, notebook basics. So how do notebooks work? Notebooks have session states that keeps track of intermediate execution results. So for example, if a user runs a cell that does something like, declaring two variables, then the notebook session state will remember that. And the session state is very handy in that it enables programs to be composed iteratively, which is very useful for tasks with a lot of trial and error, like my machine learning homeworks. So users could do something like, they will run a cell to import some libraries, load and check some data, do some data cleaning, do some feature engineering. Well, whoops, that didn't work, but that's fine because they can edit the cell code and try again. And then finally, fit some ML models. And one issue that can occur in all of this is that, notebook session states can be lost. And that is because notebook session states are stored entirely in memory. So going back to the previous case, suppose you were training that machine learning model from earlier, and if any of these things happen, like if your kernel crashes, or if you wanted to switch to a machine with more suitable resources like a GPU session, or my favorite one, which is when I was using Colab to cram an assignment before a deadline, and then I'll feel really tired, I will walk away to grab a cup of coffee, and when I come back, my session has timed out. So if either of these things have happened, then even though the notebook cells and outputs are still there, your variables are all gone, which may or may not lead to more serious consequences. And similarly, notebooks do not keep track of past session states. And what I mean by that is this is a very common occurrence in many Kaggle notebooks where users would drop stuff that they think they no longer need, like data frame columns, because sessions do have a limited amount of memory. So if they do that and they realize they actually needed those columns for later, they actually cannot undrop those data frame columns as of now. And users are very aware of these problems in notebooks. So I've seen many posts in places like Stack Overflow asking whether you can restore session states after a session terminated. And people have genuinely come up with some very creative solutions to keeping their session states alive. Similarly, people have asked about undoing cell executions. And I think even the IPython developer team tweeted about this occurrence as a joke on April Fool's Day. Okay, so what do people actually do to restore session states right now? Let's just start with the most straightforward approach, which is to rerun all the cells. So fortunately, in many of these notebook systems out there, like Colab, Jupyter, and also Kaggle, there's this very convenient button called rerun all. So when you click it, it just sequentially runs all the cells in your notebook file. And there's several issues with doing this. A very obvious one is that depending on what you have in your notebook, this might take a while. So if you are rerunning a cell that retrains a large ML model, that might not be ideal. And also rerunning cells might not always work. Users can modify cells after they were run. So in this case here, the cells that are currently in the notebook does not match the execution history of the session before it was terminated. So rerunning all the cells in this case will not give you your exact session state back. An alternative to all this is that to dump your session state before you terminate. So there's a library called dill, which is like a derivative of pickle, and in dill, there is this very convenient function called dump session, and what it does is it basically writes all the data in your session into one giant byte string and then dumps that as a file onto disk, which is called a pickle file. And if you do that and your session, say, terminates at some point, you can reload that pickle file to get all your variables back. And people have built tools upon this approach. So this tool here is called forkit. And what they proposed was to basically just use pickle to dump the entire session after every cell execution. So as you run more and more cells, you will end up with more and more pickle files on disk. And the issue with doing this might become obvious because, well, you are storing a lot of repeated data. And if you're doing this for notebook sessions, even if you're using a data frame that's like not even that large, you might end up with like, say, gigabytes of checkpoints on whatever you're storing the checkpoints on. And well, when I was running this method as a baseline for a research paper on this topic, I stored these checkpoints on Microsoft Azure, and I also forgot to delete them for a while after I completed a project. And as you may imagine, my advisor wasn't too happy about it. Okay, so can we do something that's smarter? Well, we can probably aim to manually store only the change data after a cell execution. So suppose we have a cell execution here, and if we know that all the cell execution does is declares, it declares a variable called CMB model, then we can use the plethora of, like, say, checkpointing tools out there, like StoreMagic, Pickle, or like Pickle derivatives like Cloud Pickle and dill to store just that variable and nothing else. And the issue with doing this is that correctly storing change data actually requires some degree of expertise. So I'm going to use this very simple example here where you have two variables, list outer and list inner. List outer has a shared reference to list inner. So if you separately store these two variables and then you load them again for restoration, you would realize that this shared reference from list outer to list inner has been broken. So list outer no longer points to list inner. So basically, incorrect storage can break shared references. Similarly, correctly identifying what a cell execution does is also not straightforward. The obvious case will be control flows. Well, was label updated? We won't really know without actually looking into the code execution. And another issue is hidden updates. So given that example from earlier, if another cell appends something to list inner, then in this second cell execution, list outer was updated despite never even explicitly appearing in the cell code. So while manually storing change data does sound like promising, so can we actually do something to automate a way like the requires expertise part? So that was like our idea for Kishu. So we envisioned a notebook checkpointing system that looks like this. So we would have a notebook checkpointing system on the side. The user will be running cells. For example, the user may run a cell here that imports pandas and imports the data set. So what our system does is that it would basically checkpoint on these variables. And then suppose now the user runs some more cells. The next cell does some data cleaning steps and then assigns the results to a new data frame. So instead of checkpointing the entire thing, our system will only checkpoint the change data, as we mentioned before, after the cell execution, which is like the changed data frame. So basically, our system needs to identify these so-called state deltas before and after each cell execution. And similarly, the user may run some more cell executions, like this one here, where they do some feature engineering. And then again, our system is going to checkpoint that state delta. Then, to undo some number of cell executions, for example, from that of after feature engineering to just after loading the data frames, our system can compute the difference in data between these two states and then only load the relevant data to complete this restoration process. Similarly, if the notebook session crashes after feature engineering, our system can piece back together the data that is in the session state from the various checkpoints that it has made to basically resume this session state. And the challenge left for us in all of this is that, well, how can we define these like so-called session states and state deltas? We actually need to define the granularity that makes detecting these differences and also saving and loading the data easy. And one obvious candidate that we considered at first was to basically just use variable level granularity because, well, it makes a lot of sense, right? So it's very natural to think of data in notebooks in terms of variables because it's what Jupyter Labs variable inspector shows you. It is also what tools like IPython's store magic operates on. And well, the issue that we saw with all of this is that, well, treating data at variable level granularity was what caused all like the requires expertise problems that we saw earlier. Right, so saving and loading at variable level granularity risks breaking shared references. Also, it makes cells contain hidden updates. So we had another idea. And actually, that idea came from our solution to how we would actually correctly store these two lists with a shared reference between them. So what we did is basically to correctly store these two lists, instead of storing them separately, we would basically define a wrapper that contains these two lists and then store that instead. Then for restoration, we will load that wrapper, unpack the two lists from the wrapper, and then by doing that, we have preserved the shared reference. So basically the idea is by treating reference sharing variables as a single entity, we can preserve shared references. And by doing that, we have also made delta detection easier because given that previous example where you had a hidden update, then for the second cell execution, instead of pondering which list was updated, we are just going to say that the entire thing was updated. And we gave these things a cool name. So cells no longer contain hidden updates, and we named these things like covariables, which is the term that I'm going to be using for the rest of this talk. So our system tracks and stores covariables, and it does so by maintaining a series of reference graphs, as you can see here. So these reference graphs are defined according to pickle, or more accurately, the reduce function and various object types. So basically, the nodes are individual objects and edges are references. So our system incrementally maintains these graphs, more on that later, which tracks the covariables in the session state. So as you can see from this illustration, covariables can be stored like independent data tables because there are no shared references between covariables due to the way that they're defined. So you could just pickle a covariable and it's not going to break any shared references. It also makes delta detection efficient because so suppose a user runs a fourth cell that sets object.foo equals none. So our system is going to see that object belongs to covariable number 2, which is over here. And to check for what this fourth cell execution updated, it doesn't even need to look at covariable number 1 because it knows that the users couldn't have possibly reached this covariable via referencing. Well, they can reach it through other means, but that's outside the scope of this talk. So basically, all that remains is how can we actually systematically capture all the variable references in a cell execution? It turns out that there is a surprisingly straightforward solution. And that is because a notebook session state is a dictionary. And because it is a dictionary, we can patch its getter and setter methods like this. And then whenever the user executes a cell, for example, object.foo equals none, our patch methods will tell us exactly what the user did. So what variables they accessed, what variables they assigned to. And then given these results, we will know which covariables to check for updates in. So for example, here we are going to check covariable number 2. We are going to realize that it is no longer one covariable, it's being broken into 2 covariables. So we are going to accordingly update the reference graphs and then also incrementally checkpoint the changed data. Okay, so moving on to incremental checkpoint and restore. This part is more or less like Git, so I'm going to go through this quickly. So basically what we do is we timestamp all the cell executions. For example, here, this cell here that imports the data and then also declares like an empty like machine learning model. So the delta would basically be this data frame and this new model. So suppose the user runs a second cell that fits the model. So the delta of this state with regards to the prior state would basically be this newly fitted model. It's going to inherit the data frame from the previous cell execution because, well, this cell execution did not touch the data frame. Similarly, for a third cell execution that declares a plot, the delta would be the plot. It's going to inherit both variables from the previous cell execution. Then, to undo, say, back to timestamp T1, like this, our system is going to compare these two states according to like the covariables that are in them. It's going to notice that it doesn't need to touch the data frame at all because none of the cell executions between these two states have touched the data frame. It's going to realize that it needs to update the machine learning model, GMM. So it's going to load the GMM model from timestamp T1 to basically reinitialize the model. Then, following checkout, like it, all the future cell executions will be placed in a separate branch, like here where the user fits the model with a separate hyperparameter, and so on. All right, so now onto the exciting part. I'm going to do like a short live demo of our system. So if you would also like to like check out our stuff, Kishu is open sourced on GitHub and on PyPy, so you can also pip install it if you want. But now I'm going to switch over to mirror mode to do the presentation. Okay, there we go. Oh, I have to exit full screen. 1 second. Yeah, so today, as you can see here, I prepared like a very standard data science notebook in Jupyter Lab. And to start, I'm going to start a brand new Python kernel. And the way that our system works is that you will have to initialize it. Right now, it's integrated with Jupyter Lab in the form of this drop-down menu here. You can also use hotkeys if that's your thing. So the user will click initialize reattach. And then after doing that, Kishu will start tracking and checkpointing the cell executions on this session. And we also have like another like full-fledged GUI here that you can also use that visualizes the cell executions that you have done. This is going to be updated real time as you run cells here. So I'm going to do that. So I'm going to run some like very standard data science cells like here where you import some packages. And as you're doing that, we are going to be checkpointing your session states to this like on disk database file over here. It's written in SQLite, but you can use anything else. So I'm going to run some other cells like importing data sets. I'm going to check the data frame. Everything looks normal. That's great. And now I'm going to do some like very typical data science steps like creating a new data frame without duplicates, doing some text cleaning, and so on. So as you're doing this, our GUI actually shows you like the cell executions that you've run. Like it is like collapse for clarity, but you can also expand it. All right, so at this point, I'm going to do something that many Kaggle users do, which is to drop some columns that they thought that were unneeded. So I'm going to run this. As you can see, the text columns are gone. So suppose they realized that they needed the columns for later. So without our system, you would have to go back here and run all those cell executions before this. But with our system, you can just click Kishu, click undo execution. And then what it's going to do, it is going to roll back the cell execution. It's even going to like remove the execution counter to tell you that the rollback has succeeded. And now if you check the data frame head, you can see that the text columns are back. And it will also show up here in the GUI as basically like a branch. So you've kind of went back one cell execution. So now I'm going to proceed with doing some more like feature engineering. And now I'm going to start training some machine learning models. So here I'm going to like train like a very simple multinomial MB classifier. And suppose now I'm kind of satisfied with what I have right now, but I also want to do some more experimentation, but I'm afraid that I'm going to mess up my session state. So Kishu has another function, which is called commit, which allows you to basically assign tags to specific session states. So here I'm going to commit my current session state and call it multinomial. And then it's also going to show up in my GUI here. So now I'm free to do whatever I want. For example, fit a different model into the same model variable. So I'm going to fit a Gaussian model. I'm going to check the score. Oh, it looks horrible. And I'm going to verify that I have indeed overwritten the model variable. So in order to go back to the good model that I had earlier, I can click Kishu, click checkout, and then I can check out to this previous commit that I made earlier. And after doing that, if I check the type of model, I will have seen that my session state has been rolled back to that when I made the commit. And as you can see here, well, there's a bunch of like branching cell executions. And one other thing that our system enables is that suppose your kernel crashes at this point, right? So I'm going to manually kill the session. And then, well, there's no kernel. I'm going to restart a brand new one. And at this point, if you try to like say print model, well, there is no model in the session state because everything is brand new. What you can do is, well, you can attach our system again. Find your checkpoint from earlier, and then load that. And then if you try printing the model variable, you will have seen that your session state has been restored. And well, another thing that our GUI can do is, well, you can also like basically roll back executions from the GUI directly if you want to do that. And then it's going to be updated in the notebook as well. You can also do things like, well, diffing two session states to basically see the differences in variables between the states and so on. Oh, these two states are exactly the same. Probably these two. Yeah, there we go. Okay, so back to the talk. That was a short demo. Some caveats of our system. So one thing that you might have noticed is that, well, we are relying on pickle to sort things. So, and not everything is pickleable. Some objects cannot be serialized. One notable example is generators. So if you try to pickle generators, it's going to tell you Python cannot do that. So how does the system actually handle these states? Well, it turns out that there is a straightforward solution to this. So suppose we're trying to restore to the state of timestamp T3 from whatever state, and we need to load this plot. And now suppose the plot contains the generator, so we couldn't even pickle it in the first place. So what our system is going to do is it's going to look at the cell execution here. It's going to realize that this cell execution depends on GMM from timestamp T2. So what it's going to do is it's going to load that data and then rerun the cell. So basically, our system restores these like unserializable data or data that's missing for whatever reason while replaying cells. Another caveat, so our system is limited to currently checkpointing notebook session states. So there are some notable things that we do not checkpoint, including changes to the underlying system, like packages that you pip install in notebooks, and also like changes to the underlying file system. Well, unless you customize like the reduce function of your objects to explicitly point to these things. And one thing that we definitely do not checkpoint and roll back are API calls. For example, if you use GPT a lot for your projects, and as much as we would like to do so, Kishu would not be able to like say undo your balance back into your bank account. All right, so finally, this is like a non-comprehensive list of other things that we are currently exploring. One thing is object-level duplication. So you might have noticed that I mentioned a lot about dropping data frame columns in this talk. So given this example here, if you drop 2 columns in this data frame, well, it was, according to our definitions, it would have been logically updated, right? So it's a new covariable after the columns has been dropped. But we don't necessarily want to store all of the unchanged columns as well. So one thing that we are actually exploring right now is using object-level deduplication to avoid storing within covariable unchanged data. So stay tuned for that. All right, to conclude this talk, we built Kishu, a new incremental checkpoint and restoration system for computational notebooks. It helps notebook users undo cell executions on virtual notebook states. And in order to do that, we had to address some challenges with regards to, like, say, delta detection and storage challenges, like what granularity to profile at, and so on. All right, so that's all for my talk. Thank you for listening. So if you want to try Kishu, there's links here. We open source on both GitHub and PyPy. You can also pip install it. And here's a QR code for your convenience. So of course, give us a star if you like our work. And also, there are quite a lot of technical details that I could not cover in this talk. So if you're interested in that, we do have a bunch of papers for you to read as well.